Here's a simulation I've developed of a 10 centimeter long by 1 centimeter diameter N52 neodymium magnet floating in space 200 miles above the Earth. Now, we're only taking into consideration the Earth's magnetic field and not its gravity. So the magnet doesn't have to be in orbit, just picture it floating there in space. So the magnet is set at 90 degrees perpendicular to the lines of flux over New York, or the New York latitude, where the angle of flux is about 60 degrees. The dip angle is about 60 degrees. So you can see the velocity in green that the magnet accelerates to. And you can see the acceleration in red as the magnet rotates. Now, once the magnet is set rotating, it will continue rotating for quite a while. So you'll see it get up to 1 meter per second. So just based on the magnet spinning. So this is the principle of magnetic propulsion. And the simulation is mostly mathematically and physically accurate. So this is strong evidence for magnetic propulsion, which I've been a proponent of on this channel for a long time. In fact, the name of the channel is Magnetic Propulsion. So as the magnet turns, the north end of the magnet turns faster than the south end of the magnet, creating centrifugal force, which the simulation calculates. And I'm going to show you the program in a minute. So keep an eye on this. Here's the program in Python. It's a little hard to read because of my Xbox simulator screen capture, but mostly you should be able to read most of it. If you're familiar with Python, you'll understand it. It's with the help of Cursor AI. So Cursor AI was very, very helpful with this. Now, I'm not pushing Cursor AI. I mean, if you like it, you like it. If you don't, you don't. If you like AI, you do. You don't, maybe you do. But Cursor AI is really good as far as I'm concerned. And you can see the steps of the code to see it's realistic. And you can see the math used. So the calculation is takes into account the radius of the Earth and the distance above the Earth and the magnetic field of the Earth and the magnetic field of the bar magnet, the neodymium magnet. And what it does is it calculates the integral using Simpson's rule, because to calculate the integral is much too slow. So it uses Simpson's rule to get a rough approximation of the integral of the length of the magnet and the length of the Earth, considering the Earth as another magnet, and then takes the cross product, and then you get the magnetic torque. Now, if you look here, there's a thing called torque scale, and that is the finagle factor or the fudge factor that Cursor AI put in there, and that started out at 1,000,000. And then we kept modifying the calculations, making them more and more accurate. And we got that down to 2,000. And the reason we put that in there is because we've actually seen magnets rotating in space on the International Space Station by an astronaut who did experiments with a magnet. And the magnet turns rather quickly. And with all our calculations and with the calculated torque, the magnet did not turn very fast in our simulation. So that's why we threw that number in there. So when we took into account the integration of the Earth's magnetic field, or the Earth as a long magnet, and the magnet floating in space, we got a much better, more accurate simulation as to the rate of rotation of the magnet. So then what it takes into consideration is the mass of the magnet, and then we also add a weight to one end of the magnet.